Assalamualaikum and good day. So we're going to go to the last part of chapter 2 part 3 diodes, which is about line regulations. So make sure that before you watch this recording of line regulation, please ensure that you have watched the recording or attend the lecture on load regulations. Okay. Without further ado, we go to this slide on the line regulations. Okay, so let's look at this slide. Okay, ZENER circuits analysis. So for the first analysis, of the three analysis, so we have fixed VS and RL, which are not changed. So this one we have been through. We have gone through this one for the first part, and after that we go to the when we went to load regulations. In load regulations, the VS, the source, is actually fixed, and the variable will be RL. On the other hand, for the line regulation that we will go through, the VS, the source, is actually variable, and with a fixed RL, with the fixed load resistor. Okay, so voltage regulators, as the name implies, regulators means we are going to regulate the voltage. Means it's going to have, we try to have a smooth, near to straight lines, kind of like DC outputs. Okay, so ZENER diode can act as a voltage regulator device. It maintains nearly constant voltage, so it's not constant voltage all the ranges along the range of currents. However, it will have a nearly constant voltage across its terminal. So as we know that we firstly use ZENER diode for operation in the breakdown region, which is in the reverse bias region. So here it's going to be a normal diode operations, and here is actually our interest for the ZENER diode operations. This is our starting of VZ minimum. So this is the current for the reverse currents. So when it's reached, okay, start to reach the voltage, where the start to reach the current, where the voltage will be, where the diode will enter the breakdown regions. After that, the changes in voltage is almost minimal. Okay, where small changes of voltage will give rise to a drastic increase in current. However, in terms of voltage, is almost little change. So that's why we say it's nearly constant voltage across its terminals. Okay, so this is a simple regulator circuits where we didn't have a load resistance, and after that we connect with a resistance here with RL. This is just labeling. We can put anything, but at least we know this is actually for the labeling for the load resistance, and depends on the circuits. Maybe V out is measured here. Depends on the circuit. It's not always here, but we can imagine if you want to put the output voltage, one of the ways we can put is across the RL, but it's not always there. Okay. This is a regulator circuit with a load resistance. So RS is to limit the Zener current IZ so that it is less than the maximum current IZM, because we cannot have current greater than IZM, otherwise this will potentially risk our Zener diode to be broken. So that's why we have this RS. It's a current limiting resistor. Okay. So next, voltage regulators. So how are we going to determine whether the Zener will act as a regulator or not? First, we must assume Zener diode is in open circuit, mean it is in the breakdown region. That is the reverse bias region. Zener diode is standard to operate in breakdown region. So we must assume Zener diode in open circuit for the first step. Second step, we determine the voltage, load voltage, or VL across the Zener diode, VZ. If our load voltage is much greater or greater than VZ, this diode, our diode will be turned on. Turn on here doesn't mean forward bias, it's turned on in terms of operating in breakdown region, which is in reverse bias. So hence VL is equals to VZ. Our voltage, load voltage is much less than our VL, regulation does not occur. And the VL value remains. So VL will not be equals to VZ. Okay, next. So for the line, the fixed VS and RL, need to determine the state of the diode by removing it from the network and calculating the voltage across the resulting open circuits. So I notice I have gone through this in the previous recording. You can watch them. Okay, then we're going to speed up because we want to go to the line regulation. Okay, regulations has been but in the previous recording. Okay, next we go to the last part, which is the line regulation. So this is the line regulation. So in the line regulation, what we're going to have is that our source will be fixed, it will be variable, and our load resistance will be fixed. This is in opposite with load regulation. In load regulation, the RL is variable, the load resistance is variable, and our VS is fixed. Okay. So the first step in doing the analysis involving line regulation, we get the VS mean. Okay. VS mean is what is the minimum source voltage we must have so that our Zener diode will be on, so that our Zener will be in reverse bias operating in breakdown regions. Okay, not only in reverse bias but also must reach the breakdown region, because this is actually where the Zener is considered to be on. Okay. So this is given these kinds of these circuits. So you have this as your variable resistor, variable source with this arrow, meaning it is a variable. Okay, we can vary the voltage. And after that, we have a current limiting resistor with the current passing through I1. Then we have the Zener voltage, the Zener diode, which is in reverse bias compared to our source. So this is correct. Then this is VZ in breakdown regions. So you have positive and negative here for with respect to the Zener voltage. Then we have current passing through IZ. Then we have IL, which is load current passing through our load resistor. And we measured the VL with positive here and negative here for the polarity. So let's say when the diode is already on, when the Zener diode is on, so it's like an open circuit here, an open circuit. So what we can do for the first is that we do the voltage divider rule for us to know what is our VL. So by voltage divider rule, since RL is series with RS, so we can just do accordingly. So VL is equals to RL over VS plus RL. So this is using KVL law. This is reversed by ZENER diode, so it's open, right? Then rearranging this equation, and we come up with VS minimum equals to RL plus RS times VZ over RL. So if our VS is greater or equal, if VS mean, then ZENER diode will be on. Okay, means this at this stage ZENER diode is on, so that we will get this VL is equal to VZ. Okay, VL is equal to VZ because at that time the ZENER diode is on for ZENER operations. Okay, so it's open, so they are having the same voltage. Okay, for V and VZ, because it's like a parallel connection anyway. Okay, next we're going to calculate using KCL for the two conditions. Okay, for the two conditions, we need to calculate the current passing through our ZENER diode. If our VS is minimum, okay, at time, then we will have I1 minimum. So this is proportionately. Yeah? If you have VS minimum, then I1 will be minimum. IZ will be minimum because of constant IL. Because of constant IL. Next, if we have VS maximum, it is what source is very to the maximum, then correspondingly I1 also will be maximum because resistor is constant. If V is increased, V is increased. So if VS is increased to the maximum, I1 will be increased to the maximum. So proportionally, IZ will be maximum as well. Okay. So line regulation. So you have IZ min or max. Okay, either which one we need. Then we have equals to I1 minimum passing through our resistor RS or maximum, then minus if IL constant. So this is pretty much the equations. So whether you have going to have IZ min, so you're going to have IZ min equals to I1 min minus IL constant. If you're going to have max, IZ max is equals to I1 max minus IL constant. So to get this IZ max, we will do this P equals to VI equations. So IZ max is equals to PZ max, the power dissipation at the diode maximum over the voltage of the ZENER diodes. Okay, so whereby this IL is actually VL over RL, I1 minimum is equals to VS minimum because this is minimum minus VZ, or if we are using maximum, then we change accordingly to the maximum. If I1 maximum, VS will be maximum. This is the example. Say the question, what is the range of input voltage in? So when we want range, means we want to have a value which is the other end, the other extreme is minimum, then the other extreme is the maximum. What is the range, okay, that which we should have for the V in, so that our ZENER diode will maintain regulation with current between 0.25. So this is pretty much the minimum, okay, because it's IZ minimum, and 100 milliampere is IZ maximum. So extracting the information, we have been given the IZ min 0.25 and IZ max equals to 100 milliampere. So we're going to analyze with the given value of current, ZENER current minimum, and we analyze accordingly. Then we analyze the next one with the given value of IZ maximum. So at minimum ZENER current, IZ min, the diodes to operate ZENER diode in a breakdown region. So IZ minimum is equals to R min equals to IZ minimum times the value of R, which is in this case is 220, and times is our 0.25 milliampere. So we get 55 millivolts. 55 millivolts. And then doing this KVL, Kirchhoff's law, you know that VR is equals to V in minus VZ. So in minus Vz. So V in minimum is actually VR minimum plus our Vz. Plus our Vz. So R minimum is equals to 55 millivolt. And we get the ZENER voltage 10 volts. Okay. So the answer will be 10.055 volts. Okay. So this is the ZENER voltage, ZENER diode with 10 volts. Okay, 10 volt ZENER VZ. Okay. At maximum ZENER current, let's say now we have IZ max. So we calculate accordingly for this VR max. Okay, this is VR max. IZ max R, you will get this VR max is 22 volts. Okay, 22 volts. Then again, using KVL, we know this is the condition. Then for the V in maximum, even with the IZ maximum, the R maximum plus VZ, 22 volt plus 10 volts, so we're going to have 32 volts. So this is the V in maximum we can have in order to have a consistent in order for the ZENER diode to maintain regulation, to be consistent. Okay, so this is the exercise. You can try at home, and this is the answer. This is answer. So we're going to cover this in the next class if we have time to cover this exercise. But you please do first as yourself practice at home. This is another exercise with example, with answers. Okay. So the next one is a DC power supply using IC regulators. So this is integrated circuits, which is a chip. So last step in eliminating the remaining ripples, despite having go through rectifier and filters, the output still is not perfectly like a DC level. So in order to smooth out these ripples, so we need to use the IC regulators. To maintain the output voltage to set specific values, so means that across the x-axis, it will maintain one voltage. So to a specific value. Regulation is performed by an integrated circuit IC regulator. So let's refresh back. Okay, this is pretty much the power supply. For this we have a transformer. Then we have a rectifier. In here is actually we have a bridge. Then we have a filter. Then we have a IC regulators, and this is pretty much our outputs. Okay. And the diode model used is 1N4001. Okay. The next is how we're going to calculate the regulation. Regulation is actually the measures how well the regulation is performed by the regulator circuits. Okay, regulator chip, how well it is performing the regulation. So first we go to this load regulation because this is the one being covered first before the line regulation. So in the load regulation refresh, we have a fixed Vs with a variable Rs. So load regulation is actually a ratio of change in output voltage for a range of load current values. Why we have range of load current? Because the RL in the place load resistance is variable. That's why we have range of load currents. So the load regulation is VNL. VNL stands for no load condition. And FL stands for full load conditions. Okay. So Vn minus VFL over VFL times 100%. The VFL for the VNL, we have a no load condition. So when we have no load condition, means that output voltage minimum load current because there is no load. When there is no load means there is no current to none. So we can put as a minimum load current flowing through because VNL no load. So in the no load condition, so our RL is just like infinity because there is no load. It's much likely like per second. So there is minimum load current. We can put here is IL equals to 0. In this case, like minimum, the ideal would be like minimum equals to 0. And VFL is the output voltage at maximum load current. So what is the maximum load current you can have there? Full load. Full load. In this full load current, we're going to have a maximum load current, maximum current flowing through. Next is line regulation. How we're going to calculate the regulation percentage? In line regulation, our VS is changeable, while our RL is fixed. So that's why we're going to have, in terms of line regulation, there is change in output voltage, ratio of change in output voltage, for a given change in input voltage. So here, input voltage, which is the VS, is variable. So to calculate the line regulation, is simply V out over V in times with 100%. Okay. So with that, we finish this final lecture of chapter 2, part 3. Okay. Assalamualaikum and good day.